Now that you have a pretty good understanding of algorithms and program codes, let's talk about binary numbers. Data in computers is stored and transmitted as a series of zeros and ones. These are called bits. Everything that you see or hear on the computer, words, pictures, numbers, movies, and even sound is stored using just those two numbers. This is called the binary number system, also referred to as the base 2 number system. Look at these 5 cards. It represents a 5-bit code. What do you notice about the number of dots on the cards? Each card has twice as many dots as the card to its right. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. How many dots would the next card have if we carried on to the left to make a 6-bit code? If you said 32, you're absolutely correct. It's all about multiplying by 2. That's why it is referred to as the base 2 system. If we continued on and made it a 7-bit code, 32 times 2 is 64. The next card would have 64 dots on it. We can use these cards to make numbers by turning some of them face down and adding up the dots that are shown. When a binary card is not showing, or when it's face down, it is represented by a 0. When it is showing, it is represented by a 1. This is the binary number 01001. The cards that are face down are worth 0. The ones that are face up are referred to as 1. If you add up all of the dots that are showing, you get what we call, in base 10, the number 9. What is this 5-bit code? If you said 00000, you're absolutely correct. There are no dots showing, so each card is represented by the number 0. In base 10, we simply know this number as, you got it, 0. This is a 3-bit code. What is its binary number? 111. All of the cards are facing up to reveal numbers. Therefore, each card is represented by 1. What base 10 number does it represent? I'll give you a hint. Count how many dots you see. This is a 2-bit code. You can make 4 different 2-bit binary numbers. Both of these cards are face down, so each one is represented by 0. Therefore, its binary code is 00. In this 2-bit code, one card is face down and one is face up. The one that is face down is a 0, and the one that is face up, revealing 1 dot, is represented by a 1. It does not matter how many dots are on a card. You can only use the numbers 1 and 0 to represent each card. This is a 3-bit code. In the binary system, it is called 111. Think back to the cards with the dots on them. Starting with the 0 on the right, in what we call the ones place. Do you remember how many dots were on that card? 1. How many dots were on the second card, or what we call the tens place? 2. And the third card? 4. If we use the dot counting method, this 3-bit code, known as 111, is equal to what we call, in base 10, 7. Let's try another one. This is a 4-bit code called 1001. What base 10 number does it represent? If you said 9, you're correct. Remember, the zeros equal just that, 0. How about this 5-bit code? If you said 12, you're correct. The binary
created using Powtoon.